双语音标领航，注音阅读启蒙，叶兴阳有声读物。
A History of Science, Volume 3, by Henry Smith Williams,
Henry,
LL.D., assisted by Edward H. Williams, M.D., in 5 volumes, Volume 3, Modern Development of the Physical Sciences. Contents, Book 3, Chapter 1, The Successors of Newton in Astronomy. The work of Johannes Hevelius Halley and Hevelius Halley's observation of the transit of Mercury, and his method of determining the parallax of the planets. Halley's observation of meteors, his inability to explain these bodies, the important work of James Bradley Lecale's measurement of the arc of the meridian, the determination of the question as to the exact shape of the Earth. D'Alembert and his influence upon science. D'Alembert's History of Astronomy, the astronomical work of Euler. Chapter 2. The Progress of Modern Astronomy. The work of William Herschel, his discovery of Uranus, his discovery that the stars are suns, his conception of the universe, his deduction that gravitation has caused the grouping of the heavenly bodies, the nebula hypothesis. Immanuel Kant's conception of the formation of the world, defects in Kant's conception, Laplace's final solution of the problem, his explanation in detail, change in the mental attitude of the world since Bruno, asteroids and satellites, discoveries of Olbers 1. The mathematical calculations of atoms, and Leverrier, the discovery of the inner ring of Saturn. Clerk Maxwell's paper on the stability of Saturn's rings. Helmholtz's conception of the action of tidal friction. Professor G. H. Darwin's estimate of the consequences of tidal action. Comets and meteors. Bredichin's cometary theory, the final solution of the structure of comets. Newcomb's estimate of the amount of cometary dust swept up daily by the Earth. The fixed stars. John Herschel's studies of double stars. Fraunhofer's perfection of the refracting telescope. Bessel's measurement of the parallax of a star. Henderson's measurements. Kirchhoff and Bunsen's perfection of the spectroscope. Wonderful revelations of the spectroscope. Lord Kelvin's estimate of the time that will be required for the Earth to become completely cooled. Alvin Clark's discovery of the companion star of Sirius. The advent of the photographic film in astronomy. Dr. Huggins's studies of nebulae. Sir Norman Lockyer's cosmogonic guess. Krall's prenebular theory. Chapter 3. The New Science of Paleontology. William Smith and fossil shells. His discovery that fossil rocks are arranged in regular systems. Smith's inquiries taken up by Cuvier. His ossements. Fossils containing the first description of hairy elephant. His contention that fossils represent extinct species only. Dr. Buckland's studies of English fossil beds. Charles Lyell combats catastrophism. Elaboration of his ideas with reference to the rotation of species. The establishment of the doctrine of uniformitarianism. Darwin's origin of species. Fossil man. Dr. Falconer's visit to the fossil beds in the Valley of the Somme. Investigations of Prestwich and Sir John Evans' discovery of the Neanderthal skull. Cuvier's rejection of human fossils. The finding of prehistoric carving on ivory. The fossil beds of America. Professor Marsh's paper on the fossil horses in America. The Warren mastodon.
the
Java fossil. Pithecanthropus erectus. Chapter 4. The Origin and Development of Modern Geology. James Hutton and the study of the rocks. His theory of the Earth. His belief in volcanic cataclysms in raising and forming the continents. His famous paper before the Royal Society of Edinburgh, 1781. His conclusions that all strata of the Earth have their origin at the bottom of the sea. His deduction that heated and expanded matter caused the elevation of land above the sea level. Indifference at first shown. This remarkable paper. Neptunists versus Plutonists. Scrope's classical work on volcanoes. Final acceptance of Hutton's explanation of the origin of granites. Lyell and uniformitarianism. Observations on the gradual elevation of the coastlines of Sweden and Patagonia. Observations on the enormous amount of land erosion constantly taking place. Agassiz and the glacial theory. Perrodin, the chamois hunter, and his explanation of perched boulders. De Charpentier's acceptance of Perrodin's explanation. Agassiz's paper on his alpine studies. His conclusion that the Alps were once covered with an ice sheet. Final acceptance of the glacial theory. The geological ages. The work of Murchison and Sedgwick. Formation of the American continents. Past, present, and future. Chapter 5. The New Science of Meteorology. By its investigations of meteors, the observations of Brandis and Benzenberg on the velocity of falling stars, Professor Olmsted's observations on the meteoric shower of 1833, confirmation of Chladni's hypothesis of 1794, The aurora borealis, Franklin's suggestion that it is of electrical origin, its close association with terrestrial magnetism, evaporation, cloud formation, and Dalton's demonstration that water exists in the air as an independent gas. Hutton's theory of rain. Luke Howard's paper on clouds, observations on dew, by Professor Wilson and Mr. 60R. Wells's essay on dew, his observations on several appearances connected with dew isotherms and ocean currents. Humboldt and the science of comparative climatology, his studies of ocean currents. Maury's theory that gravity is the cause of ocean currents. Dr. Kroll on climate and time, cyclones and anticyclones. Dove studies in climatology. Professor Farrell's mathematical law of the deflection of winds. Tyndall's estimate of the amount of heat given off by the liberation of a pound of vapor. Meteorological observations and weather predictions. Chapter 6. Modern theories of heat and light. Josiah Wedgwood and the clay pyrometer. Count Rumford and the vibratory theory of heat, his experiments with boring cannon to determine the nature of heat causing water to boil by the friction of the borer, his final determination that heat is a form of motion. Thomas Young and the wave theory of light, his paper on the theory of light and colors, his exposition of the colors of thin plates, of the colors of thick plates, and of striated surfaces. Arago and Fresnel championed the wave theory opposition to the theory by the French Academy's tacit acceptance of the correctness of the theory by its admission of Fresnel as a member. Chapter 7. The modern development of electricity and magnetism. Galvani and the beginning of modern electricity. The construction of the voltaic pile. Nicholson's and Carlisle's discovery that the galvanic current decomposes water. Decomposition of various substances by Sir Humphrey Davy. His construction of an arc light. The deflection of the magnetic needle by electricity demonstrated by Ørsted. Effect of this important discovery. Ampere creates the science of electrodynamics. Joseph Henry's studies of electromagnets. Michael Faraday begins his studies of electromagnetic induction, his famous paper before the Royal Society in 1831, in which he demonstrates electromagnetic induction. His explanation of Arago's rotating disk. The search for a satisfactory method of storing electricity, Röntgen rays, or X-rays. Chapter 8. The conservation of energy. Faraday narrowly misses the discovery of the doctrine of conservation. Carnot's belief that a definite quantity of work can be transformed into a definite quantity of heat. The work of James Prescott Joule. Investigations begun by Dr. Mayer's paper of 1842, his statement of the law of the conservation of energy. Mayer and Helmholtz. Joule's paper of 1843. Joule or Mayer. Lord Kelvin and the dissipation of energy. The final unification. Chapter 9. The ether and ponderable matter. James Clerk Maxwell's conception of ether. Thomas Young and luminiferous ether. Young's and Fresnel's conception of transverse luminiferous undulations. Faraday's experiments pointing to the existence of ether. Professor Lodge's suggestion of two ethers. Lord Kelvin's calculation of the probable density of ether. The vortex theory of atoms. Helmholtz's calculations in vortex motions. Professor Tate's apparatus for creating vortex rings in the air. The ultimate constitution of matter as conceived by Boscovich. Davies' speculations as to the changes that occur in the substance of matter at different temperatures. Clausius's and Maxwell's investigations of the kinetic theory of gases. Lord Kelvin's estimate of the size of the molecule. Studies of the potential energy of molecules. Action of gases at low temperatures. Appendix. A History of Science. Book 3. Modern development of the physical sciences. With the present book, we enter the field of the distinctively modern. There is no precise date at which we take up each of the successive stories, but the main sweep of development has to do in each case with the 19th century. We shall see at once that this is a time both of rapid progress and of great differentiation. We have heard almost nothing hitherto of such sciences as paleontology, geology, and meteorology, each of which now demands full attention. Meantime, astronomy and what the workers of the elder day called natural philosophy become wonderfully diversified and present numerous phases that would have been startling enough to the stargazers and philosophers of the earlier epoch. Thus, for example, in the field of astronomy, Herschel is able, thanks to his perfected telescope, to discover a new planet and then to reach out into the depths of space and gain such knowledge of stars and nebulae as hitherto no one had more than dreamed of. Then, in rapid sequence, a whole coterie of hitherto unsuspected minor planets is discovered. Stellar distances are measured. Some members of the starry galaxy are timed in their flight. The direction of movement of the solar system itself is investigated. The spectroscope reveals the chemical composition even of suns that are unthinkably distant, and a tangible theory is grasped of the universal cycle, which includes the birth and death of worlds. Similarly, the new studies of the Earth's surface reveal secrets of planetary formation hitherto quite inscrutable. It becomes known that the strata of the Earth's surface have been forming throughout untold ages, and that successive populations differing utterly from one another have peopled the Earth in different geological epochs. The entire point of view of thoughtful men becomes changed in contemplating the history of the world in which we live, albeit the newest thought harks back to some extent to those days when the inspired thinkers of early Greece dreamed out the wonderful theories with which our earlier chapters have made our readers familiar. In the region of natural philosophy, progress is no less pronounced and no less striking. It suffices here, however, by way of anticipation, simply to name the greatest generalization of the century in physical science, the doctrine of the conservation of energy. The successors of Newton in astronomy, Hevelius and Halley. Strangely enough, the decade immediately following Newton was one of comparative barrenness in scientific progress. The early years of the 18th century not being as productive of great astronomers as the later years of the 17th, or, for that matter, as the later years of the 18th century itself. Several of the prominent astronomers of the later 17th century lived on into the opening years of the following century, however, and the younger generations soon developed a coterie of astronomers, among whom Euler, Lagrange, Laplace, and Herschel, as we shall see, were to accomplish great things in this field before the century closed. One of the great 17th century astronomers, who died just before the close of the century, was Johannes Hevelius, 1611 to 1687, of Danzig, who advanced astronomy by his accurate description of the face and the spots of the moon. But he is remembered also for having retarded progress by his influence in refusing to use telescopic sights in his observations, preferring until his death the plain sights long before discarded by most other astronomers. The advantages of these telescope sights have been discussed under the article treating of Robert Hooke, but no such advantages were ever recognized by Hevelius. So great was Hevelius's reputation as an astronomer that his refusal to recognize the advantage of the telescope sights caused many astronomers to hesitate before accepting them as superior to the plane. And even the famous Halley, of whom we shall speak further in a moment, was sufficiently in doubt over the matter to pay the aged astronomer a visit to test his skill in using the old-style sights. Side by side, Hevelius and Halley made their observations, Hevelius with his old instrument and Halley with the new. The results showed slightly in the younger man's favor, but not enough to make it an entirely convincing demonstration. The explanation of this, however, did not lie in the lack of superiority of the telescopic instrument, but rather in the marvelous skill of the aged Hevelius, whose dexterity almost compensated for the defect of his instrument. What he might have accomplished could he have been induced to adopt the telescope can only be surmised. Halley himself was by no means a tyro in matters astronomical at that time. As the only son of a wealthy soap boiler living near London, he had been given a liberal education, and even before leaving college made such novel scientific observations as that of the change in the variation of the compass. At 19 years of age, he discovered a new method of determining the elements of the planetary orbits, which was a distinct improvement over the old. The year following, he sailed for the island of St. Helena to make observations of the heavens in the southern hemisphere. It was while in St. Helena that Halley made his famous observation of the transit of Mercury over the sun's disk. This observation being connected, indirectly, at least, with his discovery of a method of determining the parallax of the planets. By parallax is meant the apparent change in the position of an object, due really to a change in the position of the observer. Thus, if we imagine two astronomers making observations of the sun from opposite sides of the Earth at the same time, It is obvious that to these observers the sun will appear to be at two different points in the sky. Half the angle measuring this difference would be known as the sun's parallax. This would depend, then, upon the distance of the Earth from the sun and the length of the Earth's radius. Since the actual length of this radius has been determined, the parallax of any heavenly body enables the astronomer to determine its exact distance. The parallaxes can be determined equally well. However, if two observers are separated by exactly known distances, several hundreds or thousands of miles apart, in the case of a transit of Venus across the sun's disk, for example, an observer at New York notes the image of the planet moving across the sun's disk, and notes also the exact time of this observation. In the same manner, an observer at London makes similar observations. Knowing the distance between New York and London, and the different time of the passage, it is thus possible to calculate the difference of the parallaxes of the sun and a planet crossing its disk. The idea of thus determining the parallax of the planets originated, or at least was developed, by Halley, and from this phenomenon he thought it possible to conclude the dimensions of all the planetary orbits. As we shall see further on, his views were found to be correct by later astronomers. In 1721, Halley succeeded Flamsteed as Astronomer Royal at the Greenwich Observatory. Although 64 years of age at that time, his activity in astronomy continued unabated for another score of years. At Greenwich, he undertook some tedious observations of the moon, and during those observations was first to detect the acceleration of mean motion. He was unable to explain this, however, and it remained for Laplace in the closing years of the century to do so, as we shall see later. Halley's book, the Synopsis Astronomiae Comedicae, is one of the most valuable additions to astronomical literature since the time of Kepler. He was first to attempt the calculation of the orbit of a comet, having revived the ancient opinion that comets belong to the solar system, moving in eccentric orbits round the sun, and his calculation of the orbit of the comet of 1682 led him to predict correctly the return of that comet in 1758. Halley's study of meteors. Like other astronomers of his time, he was greatly puzzled over the well-known phenomena of shooting stars, or meteors, making many observations himself, and examining carefully the observations of other astronomers. In 1714, he gave his views as to the origin and composition of these mysterious visitors in the Earth's atmosphere. As this subject will be again referred to in a later chapter, Halley's views, representing the most advanced views of his age, are of interest. The theory of the air seemeth, at present, he says, to be perfectly well understood, and the differing densities thereof at all altitudes. For supposing the same air to occupy spaces reciprocally proportional to the quantity of the superior or incumbent air, I have elsewhere proved that at 40 miles high the air is rarer than at the surface of the earth at 3,000 times, and that the utmost height of the atmosphere, which reflects light in the crepusculum, is not fully 45 miles, notwithstanding which 'tis still manifest that some sort of vapors, and those in no small quantity, arise nearly to that height. An instance of this may be given in the great light the Society had an account of vide Transact. September 1676, from Dr. Wallace, which was seen in very distant counties almost over all the south part of England, of which though the doctor could not get so particular a relation as was requisite to determine the height thereof, yet from the distant places it was seen in, it could not but be very many miles high. So likewise that meteor which was seen in 1708, on the 31st of July, between 9 and 10 o'clock at night, was evidently between 40 and 50 miles perpendicularly high, and as near as I can gather, over Sheerness and the buoy on the Nowher. For it was seen at London moving horizontally from east by north to east by south at least 50 degrees high, and at Redgrove, in Suffolk, on the Yarmouth Road, about 20 miles from the east coast of England, and at least 40 miles to the eastward of London, it appeared a little to the westward of the south, suppose south by west, and was seen about 30 degrees high, sliding obliquely downward, I was shown in both places the situation thereof, which was as described, but could wish some person skilled in astronomical matters bad seen it, that we might pronounce concerning its height with more certainty. Yet, as it is, we may securely conclude that it was not many more miles westerly than Redgrove, which, as I said before, is about 40 miles more easterly than London. Suppose it, therefore, where perpendicular, to have been 35 miles east from London, and by the altitude it appeared at in London, viz. 50 degrees, its tangent will be 42 miles, for the height of the meteor above the surface of the earth, which also is rather of the least, because the altitude of the place shown me is rather more than less than 50 degrees, and the like may be concluded from the altitude it appeared in at Redgrove, near 70 miles distant, though at this very great distance, it appeared to move with an incredible velocity, darting, in a very few seconds of time, for about 12 degrees of a great circle from north to south, being very bright at its first appearance, and it died away at the east of its course, leaving for some time a pale whiteness in the place, with some remains of it in the track where it had gone, but no hissing sound as it passed, or bounce of an explosion were heard. It may deserve the Honorable Society's thoughts, how so great a quantity of vapor should be raised to the top of the atmosphere, and there collected, so as upon its ascension or otherwise illumination, to give a light to a circle of above 100 miles diameter, not much inferior to the light of the moon, so as one might see to take a pin from the ground in the otherwise dark night. 'Tis hard to conceive what sort of exhalations should rise from the earth, either by the action of the sun or subterranean heat, so as to surmount the extreme cold and rareness of the air in those upper regions. But the fact is indisputable, and therefore requires a solution. From this much of the paper it appears that there was a general belief that this burning mass was heated vapor thrown off from the earth in some mysterious manner. Yet this is unsatisfactory to Halley, for after citing various other meteors that have appeared within his knowledge, he goes on to say, what sort of substance it must be that could be so impelled and ignited at the same time, there being no volcano or other spiraculum of subterraneous fire in the northeast parts of the world that we ever yet heard of, from whence it might be projected. I have much considered this appearance, and think it one of the hardest things to account for that I have yet met with in the phenomena of meteors, and I am induced to think that it must be some collection of matter formed in the ether, as it were, by some fortuitous concourse of atoms, and that the earth met with it as it passed along in its orb, then but newly formed, and before it had conceived any great impetus of descent towards the sun, for the direction of it was exactly opposite to that of the earth, which made an angle with the meridian at that time of 67 gr. That is, its course was from west-southwest to east-northeast, wherefore the meteor seemed to move the contrary way, and besides falling into the power of the earth's gravity, and losing its motion from the opposition of the medium, it seems that it descended towards the earth, and was extinguished in the Tyrrhene Sea, to the west-southwest of Leghorn, the great blow being heard upon its first immersion into the water, and the rattling like the driving of a cart over stones being what succeeded upon its quenching. Something like this is always heard upon quenching of very hot iron in water. These facts being past dispute, I would be glad to have the opinion of the learned thereon, and what objection can be reasonably made against the above hypothesis, which I humbly submit to their censure. 1. These few paragraphs, coming as they do from a leading 18th-century astronomer, convey more clearly than any comment the actual state of the meteorological learning at that time, that this ball of fire, rushing at a greater velocity than the swiftest cannonball, was simply a mass of heated rock passing through our atmosphere, did not occur to him, or, at least was not credited. Nor is this surprising when we reflect that at that time universal gravitation had been but recently discovered. Heat had not as yet been recognized as simply a form of motion, and thunder and lightning were unexplained mysteries, not to be explained for another 3/4 of a century. In the chapter on meteorology, we shall see how the solution of this mystery that puzzled Halley and his associates all their lives was finally attained. Bradley and the aberration of light. Halley was succeeded as Astronomer Royal by a man whose useful additions to the science were not to be recognized or appreciated fully until brought to light by the Prussian astronomer Bessel early in the 19th century. This was Dr. James Bradley, an ecclesiastic, who ranks as one of the most eminent astronomers of the 18th century. His most remarkable discovery was the explanation of a peculiar motion of the pole star, first observed, but not explained, by Picard a century before. For many years a satisfactory explanation was sought unsuccessfully by Bradley and his fellow astronomers. But at last he was able to demonstrate that the stare Draconis, on which he was making his observations, described, or appeared to describe, a small ellipse. If this observation was correct, it afforded a means of computing the aberration of any star at all times. The explanation of the physical cause of this aberration, as Bradley thought, and afterwards demonstrated, was the result of the combination of the motion of light with the annual motion of the Earth. Bradley first formulated this theory in 1728, but it was not until 1748, 20 years of continuous struggle and observation by him, that he was prepared to communicate the results of his efforts to the Royal Society. This remarkable paper is thought by the Frenchman, D'Alembert, to entitle its author to a place in science beside such astronomers as Hipparchus and Kepler. Bradley's studies led him to discover also the libratory motion of the Earth's axis, as this appearance of G. Draconis indicated a diminution of the inclination of the Earth's axis to the plane of the ecliptic, he says, and as several astronomers have supposed that inclination to diminish regularly, if this phenomenon depended upon such a cause, and amounted to 18" in 9 years, the obliquity of the ecliptic would, at that rate, alter a whole minute in 30 years, which is much faster than any observations before made would allow. I had reason, therefore, to think that some part of this motion at the least, if not the whole, was owing to the moon's action upon the equatorial parts of the Earth, which, I conceived, might cause a libratory motion of the Earth's axis. But as I was unable to judge, from only 9 years' observations, whether the axis would entirely recover the same position that it had in the year 1727, I found it necessary to continue my observations through a whole period of the moon's nodes, at the end of which I had the satisfaction to see that the stars returned into the same position again, as if there had been no alteration at all in the inclination of the Earth's axis, which fully convinced me that I had guessed rightly as to the cause of the phenomena. This circumstance proves likewise that if there be a gradual diminution of the obliquity of the ecliptic, it does not arise only from an alteration in the position of the Earth's axis, but rather from some change in the plane of the ecliptic itself, because the stars, at the end of the period of the moon's nodes, appeared in the same places, with respect to the equator, as they ought to have done, if the Earth's axis had retained the same inclination to an invariable plane. 2. French astronomers. Meanwhile, astronomers across the Channel were by no means idle. In France, several successful observers were making many additions to the already long list of observations of the first astronomer of the Royal Observatory of Paris, Dominic Cassini, 1625 to 1712, whose reputation among his contemporaries was much greater than among succeeding generations of astronomers. Perhaps the most deserving of these successors was Nicolas Louis de Lacaille, 1713 to 1762, a theologian who had been educated at the expense of the Duke of Bourbon, and who, soon after completing his clerical studies, came under the patronage of Cassini, whose attention had been called to the young man's interest in the sciences. One of Lacaille's first undertakings was the remeasuring of the French R of the meridian, which had been incorrectly measured by his patron in 1684. This was begun in 1739, and occupied him for 2 years before successfully completed. As a reward, however, He was admitted to the academy and appointed mathematical professor in Mazarine College. In 1751, he went to the Cape of Good Hope for the purpose of determining the sun's parallax by observations of the parallaxes of Mars and Venus, and incidentally to make observations on the other southern hemisphere stars. The results of this undertaking were most successful, and were given in his Column Australe Stellium, etc., published in 1763. In this he shows that in the course of a single year he had observed some 10,000 stars, and computed the places of 1,942 of them, measured a degree of the meridian, and made many observations of the moon, productive industry seldom equaled in a single year in any field. These observations were of great service to the astronomers, as they afforded the opportunity of comparing the stars of the southern hemisphere with those of the northern, which were being observed simultaneously by Leland at Berlin. Lacaille's observations followed closely upon the determination of an absorbing question which occupied the attention of the astronomers in the early part of the century. This question was as to the shape of the Earth, whether it was actually flattened at the poles. To settle this question once for all, the Academy of Sciences decided to make the actual measurement of the length of 2 degrees, one as near the pole as possible, the other at the equator. Accordingly, 3 astronomers, Godin, Bouguer, and La Condamine, made the journey to a spot on the equator in Peru, while 4 astronomers, Camus, Clairaut, Maupertuis, and Lemonnier, made a voyage to a place selected in Lapland. The result of these expeditions was the determination that the globe is oblately spheroidal. A great contemporary and fellow countryman of Lacaille was Jean Le Rond d'Alembert, 1717 to 1783, who, although not primarily an astronomer, did so much with his mathematical calculations to aid that science that his name is closely connected with its progress during the 18th century. D'Alembert, who became one of the best-known men of science of his day, and whose services were eagerly sought by the rulers of Europe, began life as a foundling, having been exposed in one of the markets of Paris. The sickly infant was adopted and cared for in the family of a poor glazier, and treated as a member of the family. In later years, however, after the foundling had become famous throughout Europe, his mother, Madame Tenson, sent for him and acknowledged her relationship. It is more than likely that the great philosopher believed her story, but if so, he did not allow her the satisfaction of knowing his belief, declaring always that Madame Tenson could not be nearer than a stepmother to him, since his mother was the wife of the glazier. D'Alembert did much for the cause of science by his example as well as by his discoveries. By living a plain but honest life, declining magnificent offers of positions from royal patrons, at the same time refusing to grovel before nobility, he set a worthy example to other philosophers whose cringing and pusillanimous attitude towards persons of wealth or position had hitherto earned them the contempt of the upper classes. His direct additions to astronomy are several, among others the determination of the mutation of the axis of the Earth. He also determined the ratio of the attractive forces of the sun and moon, which he found to be about as 7:3. From this he reached the conclusion that the Earth must be 70 times greater than the moon. The first 2 volumes of his researches on the systems of the world, published in 1754, are largely devoted to mathematical and astronomical problems, many of them of little importance now, but of great interest to astronomers at that time. Another great contemporary of D'Alembert, whose name is closely associated and frequently confounded with his, was Jean-Baptiste Joseph D'Alembert, 1749 to 1822. More fortunate in birth as also in his educational advantages, D'Alembert as a youth began his studies under the celebrated poet Delille. Later he was obliged to struggle against poverty, supporting himself for a time by making translations from Latin, Greek, Italian, and English, and acting as tutor in private families. The turning point of his fortune came when the attention of Lalande was called to the young man by his remarkable memory, and Lalande soon showed his admiration by giving D'Alembert certain difficult astronomical problems to solve. By performing these tasks successfully, his future as an astronomer became assured.